All right. This is motivated, of course, by the those2 collaboration. The idea is to check what will happen if we include the shapes of these things that, of course, are not circular, as Matt already said. This is the outline I tried to cover in this talk. First of all, introduction on the diffraction signature of the occultation. Then testing the analytical solutions. The numerical approach we use using the flash Fourier transformation algorithm. The observation parameters, shape effect on light curves, more shapes, and some takeaways. So let's see what we can get from here. So first, we are talking about blind sorting. So when we have we are lucky and we can predict an occultation, what we do is to take all of our gear and just deploy and be ready. And even with months of planification, some things can be wrong. Maybe the weather has happened to us, Mark. But anyway, the thing is, with blind survey, we don't really have one core, one visit, and we have to determine at least the distance and size of the object in order to give some result. What we know a priori is the star type, magnitude, apparent size, the opposition angle, the cadence of the observation, but we don't know everything else. Impact parameters, breathing directions, size, distance, and shape. But shape can influence the results of the distance and size, and that's why I'm talking about it now. So we started this work in 2019, I think we published it, but Matt convinced me to give a talk related to it because I haven't finished the final pipeline. So it's like a pressure thing to finish that. It's almost done. So just to highlight what Matt already said, distance and size are entangled. So the greater the size, the larger the object, the deeper the profile. However, when we go far away, like 500 AU, we will get a shallower profile. But depending on the size, it will become again deeper. So we cannot disentangle this relationship. This is a compromise. So I was about to explain this, but Matt already did. So I will skip it and finish quickly to go to dinner. Well, what happened? This is basically what is happening. We have a plane wave that is coming into obstruction, and the wavefront breaks when it touches the obstruction, right? So in each part, well, depending on the wavelength, we will produce a lot of point source around the edges, separated by this distance. But these are irradiating light in all directions. So each part or each radiator here will contribute to all of this diffraction profile. So that's the complication of this. And when we detect something in density, we lose the information of the phase. And of course, if we want to detect the electric field, and we can basically model it using the phase. But when we detect it, we will use the phase because we have to take the modulus, the square thing of the electric field. And there is an analytical solution for that diffraction equation. That because the difficulty is to take into account all the radiators around the edge of the obstruction. But if we constrain the things to a circular shape or other geometrical shapes as Broca's and Nikkei 1984 and 2007. This basically give a solution for this equation, which is a simplified equation. It's not a full diffraction integral. And he did it through the Lambda equations. So we have an analytical solution, but only for circular objects. But what happens if we have something like the 67 comet in the TNO region? So the way to do that is we take the transformation of the object, the Fourier transformation of the object, and multiply it by a factor, phase quadratic factor, and then we go back and take the inverse transformation to get this one. So I challenge you to tell me which of these profiles, if we have a telescope, this is a projection over the Earth. The diffraction pattern is actually projected over the Earth, and the telescope is passing in this direction. So tell me, which of these belongs to this shape? This one or this one? Same size, same distance, but different shape. Who says this one? Hey, great. Who says this one? This is for, but actually both are wrong. The thing is, this is a simulation for like a contact binary, a peanut shaped thing, and this is a circular one. It's pretty symmetric, and this is not symmetric, and this is less symmetric than these two. So this is the real result of the diffraction profile taken from this diffraction pattern. So these red lines are the real size of the object without taking into account the diffraction profile. So the question is, these are profiles. These are not real lighters. We still have to sample them. So you need to have a very high cadence to get these features. So if we have that already, because I didn't say that, but it's not exact. It's an approximation, a numerical one. But we tested using the analytical solution. This is the result from Mihei in 2007. And we simulated with our algorithm. More or less it works. If you give more points to define these diffraction patterns, we will increase the residuals. But anyway, basically it works. And what you can see here is the difference between the effect of the final source due to basically the size of the star over the object when the occultation is happening. I will explain that a little bit more in 2 seconds. So, apart from this, well, besides the distance and shape, there are other constraints. Of course, the stars are not lasers. It's not monochromatic things. What we have is a band of wavelengths. And we have to take into account the radiation profile of the star, and the filter and the camera, and the combination of all these three to have this band. But we can see that the effect is not so bad, it's not so strong. But if you go to the size, to the finite size source thing, things become very complex. It's not the same to have one LED shining on us that having many. This is what happens when we have non-point source, a final source. Because instead of having just a source of light very defined, we will have like a lamp illuminating the object. So it's like to have a lot of small point sources around. So each point source will produce a diffraction pattern. Yeah. But in different positions. So you have to average all of them, and that will wash out the the diffraction signature. So this is what we get in the diffraction profiles. This is for a big star, but all of these are for the same apparent magnitude, let's say 13. And since we have big star, it has to be very far away for us to have the 13 magnitude. But for M star, that is a small star, it has to be very close to us, and it will be bigger. So that will generate this profile, very shallow. So if we try to observe only this kind of stars, we will fail. So we won't have enough information to determine the size and distance. So the other thing is, Matt already mentioned that the Fresnel scale is a measure of how big is the diffraction pattern. How big is the diffraction spread out of the center of the object, So it depends on the distance and on the wavelength, of course. But taking 600 nanometers of wavelength, we can calculate this. So you can see that for different kinds of stars, the spectral type of stars, and different distances, we have for different magnitudes the Fresnel scale, not the Fresnel scale, the apparent radius of the star will be bigger. So there is like our rule of thumb. If we have the apparent magnitude more or less the size of the Fresnel scale, more or less the half of the size of the object, we will lose every chance of getting the profile. So I will finish this quickly. This is a circular object. This is a contact binary object. And the other thing we haven't taken into account is the reading direction. If we change the reading direction, it won't affect the circular object, but it will affect other shapes, and we will get these things. Even here, this is an occultation, and it has a spot instead of a dip. So if we go to actual light curves without noise, I have to point out that for this presentation I didn't add any noise. You can see for the small objects, everything is mixed. So you cannot detect between binary objects. The red ones are binaries, contact binaries, and the blue ones are circular objects. So you cannot differentiate them until you get, well, these are different impact parameters. This is the core where we are reading it. So in this case, we can differentiate everything, and from here, we cannot say most think that we have something, nothing about the shape. And with what if we go to an ellipsoid object? So we will get this profile, this diffraction pattern, and this ellipse, well, this light curve from the ellipse. So if we change the reading direction, we will have a completely different profile. But if we change to the final source thing, we will mix everything. So we won't know anything about the shape because we wash out I think it was ringing the bell. we will lose all the information of the diffraction. Yeah. Okay, so this is another shape of binary, separated. This is for a point source and monochromatic thing, event. And we add the bandpass and the final source, we will get these profiles and these light curves. So, more or less we can conclude this. And I will take questions if it's time. There's time.
Do you have an idea how many parameters do you need to actually
like 7
lighters?
Like 7 plus the reading direction.
So including for binary objects, right?
Sorry?
Including the case of binary objects, you need only 7?
But you asked me about the parameters, right?
Yeah, let's say you have data flowing in,
Mhm.
and you need to say, okay, we have something here, what it is. It's a binary with two parts, coordinated in this way.
I have a tool that I haven't told Matt about that, but I have to report. I plan to upload that web page to have that tool for simulating and feeding manually the curves by drawing the thing by yourself. So it will depend on your artistic, but it's a tool. You can do it.
Hey, this is scary. I gotta say, this is scary. One of the criticisms that Helga received for her occultation detections, which many people believe back in 2012, was how far away the data points themselves were from the circular shape models themselves. Despite the fact that she had nice dips and stuff, it didn't really look like the area patterns I could see. I'm wondering if this work provides a little bit more credibility to her detections, because you're demonstrating here that you really shouldn't be using spheres. What do you think?
Let's model it and see. Yeah, I think we can do it.
Yeah. Well, Toka's detections were about 1 kilometer diameter, if I recall correctly. And that's sort of the regime where the shape doesn't matter all that much to the light curve shape.
Any more questions? No? If there are no more questions, we can finish the day for today. Have a good night, and just say thank you to